Hello, in this podcast we're going to take a look at gravitational forces, specifically Newton's law of universal gravitation and gravitational force fields. So Newton discovered that objects with mass exert gravitational force on each other. So mass 1 and mass 2, they don't have to be planets or stars. It can be any two objects, and they can be anywhere in the universe. So that means that you exert a force of gravity on the objects around you because you have mass. Gravity is a non-contact force. It's the weakest of the four fundamental forces, with electrostatic being the strongest. And it's an action-reaction pair, which means the force of mass 2 acting on mass 1 is just as strong as the force of mass 1 acting on mass 2. Sir Isaac Newton here is exerting a force of gravity just as strong on the Earth as the Earth is exerting on him. But as he falls to the Earth, we're not going to notice the Earth being pulled up towards him because the Earth is so much more massive than he is. Let's take a look at the actual law, and its force of gravity is equal to G times capital M, lowercase m, divided by r squared, where G is the gravitational constant. Its numerical value is 6.67 times 10 to the negative 11th newtons meters squared per kilogram squared, or if you want to write it in the base units, meters cubed per kilogram second squared. Capital M is the mass of the larger object in kilograms, lowercase m is the mass of the smaller object in kilograms, and r is the distance between the object's centers of mass in meters. Now, a couple things to point out here, that we can use this equation anywhere in the universe. And when it came to this gravitational constant, Newton knew that it existed, but he didn't know the exact value. Cavendish did an experiment in 1798 to find this out. Sometimes in the equation you'll see m sub 1 in place of capital M and m sub 2 in place of lowercase m. And lastly, remember to convert your kilometers to meters, especially when you're studying bodies in the solar system and beyond. Your distances are going to be in kilometers and you need to convert them to meters. So let's put this law into action. How attracted are we to earthly things? Calculate the gravitational force of attraction for a 100-kilogram man standing 3 meters away from his 2,500-kilogram pickup truck's center of mass. Well, we go ahead and use the equation. We plug in the universal gravitational constant, the mass of the pickup truck, the mass of the man, and the distance between their two center of masses, and we get a really small number. 1.85 times 10 to the negative 6 newtons. So in answer to this, how attracted are we to earthly things? Not much. Let's take a look at another problem. How strong is Earth's gravity pulling on the moon? Now, when we get a problem like this involving the planets, moons, and stars, we're going to need this kind of information about the orbital distance as well as their masses. And we need to remember to take all the distances, which are usually in kilometers, and convert them to meters. We can go ahead and plug in our universal gravitational constant, the mass of the Earth, the mass of the moon. Now, in the denominator, we need to remember that this r squared here is the distance from center of mass of the Earth to center of mass of the moon. So we need to add all three of these quantities together, the altitude being the distance surface to surface. And we wind up getting 3.8 times 10 to the 20 newtons. So when we have massive bodies, we have massive forces. Let's take a look at a very important law in physics, the inverse square law. Gravity obeys this inverse square law because the distance is squared in the denominator. And this law applies to quantities that emanate radially from a source. So here we have a source. Quantity radiates in all directions. Examples of quantities that follow the inverse square law are, in addition to gravity, light, sound, radiation, and electric fields. And let's just take a little closer look at this law. We have the quantity starting with very intense at a source, and it spreads out radially in all directions. And of course, if you can think of the shell as it radiates out, think of this quantity being spread out amongst a shell that's getting larger and larger in radius. And that shows you right here. You can see that the intensity is decreasing because the amount of the quantity here, another radius away from the source, that same quantity or same amount has to be spread out over a larger area. And as you continue to move away from the source, that quantity gets spread out over a larger and larger spherical area according to this formula. And that's what leads us to the inverse square law. The intensity drops off quickly as you move away from the source. And you can see in this graph here of relative intensity versus relative distance, notice it drops off precipitously so that when you increase the distance by a factor of 10, you are decreasing the intensity by a factor of 100. Let's take a look at gravitational force fields. So non-contact forces create force fields. Objects with mass create gravitational force fields. And a field exerts a force when another object with mass enters it. So here's a diagram of Earth's gravitational force field, and these two objects at point Y and X are inside the field, so Earth's gravitational force field is exerting a force of gravity on these two objects and pulling them to the center of the Earth. I want to take a moment and point out the differences between classical Newtonian physics and Einstein's theory of general relativity. Newton found that objects with mass exert a gravitational force, which caused the smaller object to move towards the larger object. Einstein's theory of general relativity shows that objects with mass warp space-time, and it's this warping of space-time that causes the smaller objects to move towards the larger massive objects. And that's why we see galaxies and stars being able to bend or deflect light. In all cases except objects moving close to the speed of light, classical Newtonian physics handling of gravitational forces works just fine. But we need to use Einstein's theory of general relativity to understand why galaxies and stars can bend light. Force fields extend an infinite distance. That means any object, the Earth or even you, your force field goes out to infinity. Of course, though, as we learned from the inverse square law, the field strength decreases rapidly with distance. So, for example, the Sun and all the planets and moons in the solar system exert force of gravity on our oceans. However, only the Moon and Sun's gravity forces have a noticeable effect on ocean tides. The gravity forces for the rest of the solar system have no noticeable effect. I want to make 2 points about this diagram for the gravitational force field. First, the gravitational field strength is constant along any concentric circle because it's the same distance from the center of mass. And secondly, the field strength decreases as you move to concentric circles that are further away from the center of mass. Let's move on and look at calculating the gravitational field strength. And to do this, we combine Newton's second law of motion and Newton's law of universal gravitation. So here are those two equations. We've customized Newton's second law for force of gravity. And we go ahead and set them equal to each other. Do some manipulation, and we come up with this expression that allows us to calculate G, the gravitational field strength, anywhere in the universe. Here's an example of how we can apply this equation to the Earth. So notice at the surface of the Earth, we can go ahead and plug in the mass of the Earth and the distance from the center of mass, and we come up with 9.8 newtons per kilogram for the gravitational field strength. We can move out to the International Space Station, which orbits about 250 miles above the surface of the Earth, and G is 8.7 newtons per kilogram. We can go all the way out to the Moon, which is 240,000 miles above the Earth's surface, and we can see that the gravitational field strength drops off precipitously. And of course, the gravitational field goes off into infinity, but at a distance of infinity, the gravitational field strength is 0. Let's move on and give you a chance to calculate some gravitational field strengths in our solar system. Here we have a list of some of the major bodies in our solar system, along with their masses and radii. Pick a couple of these bodies and go ahead and calculate the gravitational field strength at their surfaces. Pause the video now to do your calculations and then come on back and check your answers. Well, how did you do? This wraps up our lesson on gravitational forces. Let's go ahead and summarize what we've learned. First, gravity is the weakest of the four fundamental forces. It's a non-contact force. Newton's law of universal gravitation allows us to calculate the gravity force between any two bodies anywhere in the universe. The inverse square law is an important law in physics because it applies to any quantity that emanates radially from a point source. Objects with mass create gravitational force fields, and the gravitational field strength can be calculated anywhere in the universe for any object using this relationship. Well, this ends the podcast. I hope you found it helpful, and have a good day.